Hi, thanks for the introduction, Julio. So the work, as you've heard from the title, intersects two topics. It's about visualization, which I trust you all know something about, and then it's about large wall displays, or more specifically, research on large wall display interaction. And if we look at wall display interaction, wall displays in general, they've been used for a number of different use cases. InfoVis, we see a SciVis application there. There's meeting settings, lots of use in public displays. In general, they're very large surfaces. We have 10 square meters or more. These days, they're mostly interactive, so they support touch. Often they support things like tangibles, pen. You could interact from the distance with a smartphone, maybe using distal pointing, things like that. They have a resolution that's so high that it cannot be entirely perceived from one position, which means users move around. They move around for several reasons, but one of the reasons is that then they can see all the pixels. And the walls are big enough that what is displayed on them is usually public or semi-public because, well, you can look over people's shoulders and just see what's there. Now, if we look at how people have researched wall display interaction, they've, of course, looked at lots of application cases. Then there's research on collaboration. This is by Jacobson and Hornbeck. There's research on how people move around, locomotion, or more specifically, physical navigation, moving around to access data. And then we had a paper last year at ISS on awareness. If one person is interacting at a wall, collaborating with somebody else, does this other person actually know what the first person is doing? Now, in a lot of cases, people use video coding to analyze what people do at wall displays. And that's, so there's several hours of video, and the largest I found is the Jacobson and Hornbeck paper. They had 24 hours of video they were coded. Video coding involves going through videos multiple times, and everybody who's done that knows that that's incredibly time-consuming. So we went through that process as well. We didn't entirely code the videos, but we analyzed the videos at least and figured out, well, can we do better? So our research question is, what visualizations would allow us to understand multi-user interaction at large display walls more effectively? And there's several challenges here. First of all, we wanted to support time periods, because if you only see one point in time at a time, you have a speed problem when you're looking at 24 hours of time. We need to provide some sort of dimensional mapping because most of the data is three or more dimensional. You have three-dimensional positions, you have the time, you maybe have things like gaze positions on the display in addition to time, things like that. And we wanted to support the relevant research topics, which I just sort of went through a few of: collaboration, locomotion, awareness. Now, other people have obviously done tools for interaction analysis, and close to our work are two sort of types of tools. First are the video coding tools that allow you to annotate videos quickly. Like, for instance, vcode and vdata, of which we see a screenshot here. And then there's tabletop visualization toolkits like VizTaco, in this case, which shows touch traces on of touches on a tabletop display. Now, video coding tools have the issue that the same speed issue that you cannot view regions of time at once. And tabletop visualization toolkits are specific to tabletops, which, for instance, don't have this issue of people walking around a lot. So yeah, we look through this, and I'll just jump right through to the results. This is our Group Interaction Analysis Toolkit, short GIAnT, which shows a number of different views of our data. And they're all synchronized to a current point in time and to a current time period. What we see here is, I'm not sure if you can read the lines. It's about 5 minutes of interaction. But users can pan and zoom in and out interactively. I'll show a live demo of the software later on. This is open source. The URL is there. It's on GitHub. What we have is a time slider that shows you, well, the current point in time and the time period that you're looking at. There's this play button that allows you to play back in real time. Oops. Yeah, this is the one I want. Where you can look at the video. We have a view of time versus the position across the wall. We have a view of gaze positions on the screen and touch positions on this wall display as well. And then we have a view of the positions on the floor of the people, both done as heat maps, so we can see the distribution over time. Finally, we have a statistics view that shows you some aggregate data of the time period you're looking at. Going into more detail, the timeline view has, well, time at the bottom axis. Vertical axis has the position across the wall. And what happens now is we've used both our screen dimensions. So distance between users is lost. What we did to solve this is we code the distance from the wall as the width of the line. At that point, viewers still have a good idea of the distance between the users, or for instance, things like social proxemic zones. In addition, we have white dots on the lines. These are the touches on the wall. And the way we code the colors, now unfortunately this isn't really visible on the projector. On a well-calibrated screen, you can see that the users all have equal perceptual brightness. We coded the colors in LCH color space, and we use different hues to differentiate the users. That means brightness is there available to code other variables, and we coded the distance from the wall as brightness as well. Now, things you can see here, for instance, if you look at the beginning, you can see there's not much movement for the first few seconds, and that the users are standing a bit farther from the wall. Or right about at the end, the green user is at the back, and he crosses over, walks behind the other users. So you can see that from the visualization already. We have an alternate timeline visualization that puts focus on the distance from the wall. Now the vertical axis is the distance. So we lose the distance from between the users, but we can still see switches between, for instance, overview and detail work on the wall. Yeah, the white dots are still touches. Going to the wall view, we have a color-coded heat map of gaze points. And a scatter plot of touches. You can see the touches here. Again, LCH color space. We use additive blending so that regions with overlapping users are brighter. And you can see things like can users actually see where other users are touching. For the floor view, we have a heat map of user positions again. So we're looking at the wall at the space before and in front of the wall from the top now. You see the current positions as dots and viewpoints as lines again. So yeah, and what I'll do now is do a short walkthrough of an analysis session using the actual software. I've enlarged the mouse cursor, as you can see. Yeah, so this is the software. We can pan around the time. We can zoom into it. And we can have the video running. And then everything changes as people move around. So if we, just from the overview here, we can see that, well, most of the time, people have this sort of configuration where they're close to the wall, and they're all in one group. They're switching positions pretty often. It doesn't seem like any one player is being left out. This is actually an important point. This is a game we have as an example. This is a cooperative game. People have to work together to solve an issue, which is also why they're sticking together and watching each other, what they're doing. We can also see this, there's different phases. There's this phase at the beginning where the users are pretty far from the wall. There's a phase at the end where they're pretty far from the wall. And, well, most of the time they're close together. And there's this small little place where they're spreading out and coming back together again. From the heat maps, we can see that, well, there's a hot spot here. There's a hot spot here. But mostly, they've used all the wall. As they get to the back, they sort of gravitate towards the middle. But there's a lot more interaction at the front than at the back. We can see that. Now, to get to a bit more of a precise analysis, we go. We can zoom in and look through the phases by just panning around in time, and we can sort of see that the interaction that for instance the gaze points move with the players, and that there's usually a large white spot, meaning this is where everybody is concentrated. There's not many spots that just one person is seen, so they're all looking at the same place. This goes on until we get to the point, I'll zoom out a bit to get to this strange thing here where they're all spreading out. And, well, they're standing there doing nothing. If you start the video now and the sound, which I won't do, then you can see that there's a game element that they're looking for that's missing in this dark part of the wall, and they decide to spread out and find it. You can see they're not looking at the same point here either, and that they're covering the complete wall. And if we can look at it in the video as well and see that they're actually walking around searching for the last game element here. They found it, and they can solve the game now. So yeah, that's sort of a walkthrough of how you can do analysis using this. Behind the scenes, this is our software architecture. So you've seen the visualizations. We also have our data sources beneath that, and from the data sources, we calculate some derived data. So if we look at the data sources, you've seen we need the positions of the users, their gaze direction. We need to know the touches on the wall, and more precisely, we need to know user-coded touches. We need to know who is touching. And then what? We need a video feed, obviously. What I've just been talking about is the abstract data sources. We still don't know where we get the data from. That's intentional. We'd like to have a toolkit that's abstracted from that. In the current implementation and what we used for the example you just saw now, we used the concrete data sources, marker-based tracking, so we gave the people caps. You saw that maybe in the video. And to get the user position and to, well, estimate the gaze direction from head direction. The touch is, in this case, done using tangible markers. So users place tangible marker on the screen to open up a an interaction area that is then user-coded. Obviously, we can change all that. We could use the marker-based tracking to tell us who's touching, or we could use a connect-based system to find out who's using the wall as well, where the people are. Behind the scenes, we're using Python and the libavg framework. The data is in an SQLite database. Some of the visualizations are done in C++, so they actually have the interactivity you saw. And there's a preprocessor script that takes all the device-specific data and turns it into the abstract data. As I said, it's open source. Here's the URL again. It's licensed under the GPL license. Feel free to fork it, to install it, to visualize your own data with it. If there's any issues, feel free to contact us. We'll be glad to help. Yeah, so concluding, these are our contributions. We contributed a set of visualizations for wall interaction analysis. We're able to show interaction over configurable time periods. We have an intelligent mapping from high dimensions to lower dimension. And we support the research topics that are current in wall interaction research. In addition, we contribute the group interaction analysis toolkit, GIAnT. It's open source. It's expandable to new visualizations. You can add new data sources. You could add new statistics as well. And yeah, that's it for me. Thank you. Shameless self-advertisement. I'll be finishing my PhD at the beginning of next year. So if you're looking for a motivated postdoc, talk to me. And I'm happy to take questions.
Thank you very much, Ulrich, for the nice presentation. Are there questions? I have one ready. So here we have one question.
Hi, Tim Dwyer, Monash University, Australia. Nice work. Looks like a really nice tool. And I was all excited to download it and try it out. And then I realized that, unfortunately, our display walls at my university aren't flat. They curve around,
yeah,
and things like that.
Yeah.
Have you thought about how you would design your tool differently for curved display walls?
Actually, I think as long as you're, I mean, it wouldn't be I actually met somebody who's doing museum work and has the same issue. You need to map the dimensions. So if the wall is not flat, you make it flat for the visualization, and you map the user positions. That won't tell you everything just as well, but it might still be able to well, it still tells you things, the dynamics over time are pretty clear in that one view. And I haven't seen an alternative that makes it that clear. So maybe try it. Is it the qubit wall that you're talking about? Or?
No, full wraparound.
Oh, okay, okay.
Stopping.
Okay, yeah, that's when that might get hard, yeah.
And the other place I was thinking is in virtual environments, you know,
Okay,
live and things like
yeah.
that.
Okay, yeah, cool.
More questions? Yes, sure.
Basically, I'm supposed to announce my name, Marilyn Tremaine, Rutgers University. Scientific visualization in general is looking at ways to present visualization so people can get new concepts or understand the data in new ways, and that's a really hard problem. And my question is, did you have anybody looking at those visualizations and making some insights into what might be happening in the collaboration and sort of trying to generate theory?
So the question is, how is this applicable to the collaboration things? Yeah, I think there's a lot of, like, what we looked at specifically wall display collaboration, but there's a lot of these things that could expand to different collaboration issues, yeah. We could, one thing we looked at, which we unfortunately don't have in here at the moment, is, for instance, visualization of F formations. You could change the time visualization to display when two people are actually in an F formation, so, or in which F formation they are, things like that. So there's, and things like the awareness issues that you're looking at the same spot. I think there's a lot of collaboration issues that you're looking at, yeah.